Virtual sensors based on artificial intelligence can massively reduce system complexity and development costs. But how can we integrate them quickly and reliably into safety-critical applications? Welcome to today's hands-on walkthrough. My name is Lars Wallbaum. I'm a software developer for TargetLink here at dSPACE. Today, I will show you how you can bring a virtual sensor given by a neural network into your safety-critical application on your ECU. We will do this with TargetLink 24B and a model-based ISO-certified TargetLink workflow. First, let's discuss the goal of today's task. AI in automotive vehicles is typically connected with the field of automated and autonomous driving, where camera, LiDAR and radar data is recorded and processed to analyze the environment of a vehicle. The neural networks used in this area are large and require high computing power to run. However, we will focus on smaller neural networks, for example, to realize virtual sensors. Virtual sensors can replace a hardware sensor by a software-based solution, which estimates the desired property based on other sensors which are much cheaper or are available anyway. Examples of virtual sensors are the estimation of emissions from combustion engines based on the current fuel intake, or the estimations of tire pressure based on the temperature of the tire and the wheel speed. Another example of virtual sensors that we will use today is a sensor that predicts the state of charge of a battery. The question that arises is how a virtual sensor realized through a neural network can be incorporated into a safety-critical ECU application in a vehicle. Before we go into the integration part, let's quickly look at how these neural networks are usually developed. This is typically done with the help of a corresponding framework such as PyTorch or TensorFlow and fed with training data. Obtaining the right training data is crucial for the development process. For a virtual sensor, this could be as easy as just building the actual physical sensor that you want to replace into a prototype vehicle and measure the real output. Training based on this data is carried out with the help of the used framework on powerful computers. During the development of neural networks, optimization steps can be carried out repeatedly to improve the functionality of the network. The integration described here starts at the point where the neural network is adequately trained, enabling you to select any framework of your choice for its development and training. For this demo, we will use a neural network that was developed with the Keras framework. This network is trained to predict the state of charge, or SOC, of a battery. As inputs, it takes the measured voltage, the current and the temperature. To be independent of the used training environment, the neural network was exported as an ONNX file, and it was ensured that the ONNX representation behaves in the same way as the Keras model. To integrate this model into TargetLink, we use a custom code block with a new feature introduced in TargetLink version 24B, adaptable behavior. This feature lets you choose any file that defines the desired behavior of the custom code block. In our example, we choose the ONNX file for our model that was exported from Keras. But this feature is not limited to ONNX files or even neural networks. This could be just about anything from text files to spreadsheets or anything that holds the data necessary to describe the desired behavior of your custom code block. What makes the adaptable behavior interesting is that you can pair it with an implementation function. This function is a MATLAB script in which you can specify what needs to be done to implement your behavior in the custom code block for TargetLink. In our example, this script executes an in-house tool from dSPACE to generate the required C code for the ONNX file. You can see the external code generator being executed on the command line when I click on this button. Being able to call this once is nice, but the adaptable behavior feature also comes with a built-in up-to-date check. TargetLink will run this up-to-date check before generating code and ensures that the implementation matches the latest version of your neural network. Lastly, a build extension can be specified for this custom code block in your data dictionary. This lets you choose different source files that TargetLink should use depending on your current target. For example, in this case, I have one set of files to be used for a generic target, but I have also specified different files to be used for a target with an ARC processor. These files can contain target-specific code that would not compile on other targets. Using a build extension allows you to switch between different targets without needing to adjust anything in the model or data dictionary. Now let's do the simulations. We start with a model in the loop or MIL simulation. For the MIL simulation, this block is configured to use the ONNX runtime as a reference implementation of the neural network. This is done using an S function under the TargetLink custom code mask. After MIL, we can do the software-in-the-loop or SIL simulation. For this simulation, TargetLink generates code for the surrounding model and compiles it together with the externally generated code for the neural network. After SIL, we can do the processor-in-the-loop or PIL simulation. For this simulation, TargetLink compiles the code for a selected target and flashes it directly to the connected hardware. We can see that the build extension now selects the files with the target-specific code. After having run all simulations, we can compare the respective results. As we see in this graph, there are very tiny deviations in the output in the order of 10 to the power of minus 15, which is about the precision of double floating point types. Such deviations can always appear due to floating point operations being executed in a different order in the simulations. For the PIL simulation, this occurs since the target is using a vector unit as an accelerator. But we can see that these effects are small enough to not affect the overall precision of the output of the neural network. With this, we have successfully done a back-to-back testing for our neural network. We have verified that the neural network that was deployed to the target behaves the same way that it did in the original training environment. The neural network is now available in a TargetLink model, which can be extended with our well-established model-based development approach. This means you can now model the system that consumes the predicted outputs of the virtual sensors as you would do with an actual physical sensor. So, what have we learned today? We have seen how to use the new features of the TargetLink custom code block to easily embed externally generated code into TargetLink. How this integration can be automatically kept up to date. We have seen how to use build extensions to easily switch between SIL and different PIL targets. Most importantly, we have shown how externally developed components like neural networks used for virtual sensors can be seamlessly integrated into the established TargetLink workflow. Finally, we can use the ISO-certified TargetLink workflow to bring these components into safety-critical systems. Thank you for watching this hands-on walkthrough. If you want to know more, please have a look at our other videos or contact us directly. Have a nice day.
dSPACE, your partner in simulation and validation.